Okay, I'm back here. Hi again. We are going to continue part two of read along Chris Ola's blog about RNN, Recurrent Neural Network, and LSTM, long short-term memory. Um, I forgot where we stopped the last time. I think we did that. Yeah, I think we did this, the core IDB and LS. I think we just halfway. Yeah, I think we did this one too. Okay, I'm just gonna continue from here. I think it's from here. Okay, so the LSTM does have the ability to remove or add information to the cell state. Okay, carefully regulated by structures called gates. The gates are this called gates. Basically a neural network plus point-wise or element-wise matrix multiplication. That's called a gate. Okay, gates are a way to optionally let information through. Optionally, so it's not a mandatory, because sometimes when you have an information uh, by because this is a pointwise multiplication, right? If it's a matrix, for example, by multiplying a specific variables, it can be attenuated. It could be like make it like disappear, right? Let's say you multiply it by, let's say, I don't know, or negative, even negative, right? Because this is the output from the sigmoid function, which is basically from 0 to 1, I think, right? So anything that's below 0, so if you have negative 1 to negative 2, negative 3, it's going to be squashed into 0. Anything that above 1 is going to be squashed into 1, right? So that's what it is. And then, um, okay, we'll see how it works. So, but it says it's optionally let information through. They are composed out of a sigmoid neural net layer and a pointwise multiplication operation. So that's called gates. This whole thing is called gates. Okay. The sigmoid layer outputs numbers between 0 and 1. Okay. Describing how much of each component should be let through. A value of 0 means let nothing through, while a value of 1 means let everything through. Okay. An LSTM has 3 of these gates. Okay. To protect and control the cell state. Yeah, like I said, the sigmoid worker actually is the hard working worker, because we have two kinds of worker here. Remember, we have the sigmoid worker and we have the 10H worker. The 10H worker is kind of lazy. He just give his output to one of the multiplication machine, right? While the sigmoid worker, he works really hard. He works 3 times as hard as the 10H worker. He give it to 3 um, machines, multiplication machineries. So basically, it's forming a 3 gates of sigmoid gates and only one of a 10 heads gates, right? You can view it like that if you want to. Okay. Um, so has 3 of these gates to protect and control the cell state. Hmm. You have to elaborate more on this, the meaning of this, to protect and control the cell state. Step by step LSTM walkthrough. All right. The first step in our LSTM is to decide what information we are going to throw away from the cell state. Okay. This decision is made by a sigmoid layer called the forget gate layer. Okay. It looks at the HT minus 1, so the previous like time step just before that, and XT. So you can see this one over here, HT minus 1, right? And then the XT. It's merging, so it's being concatenated. Remember, if it's merging, this one is being concatenated, right? Um, so this is like the output from the previous time step. Remember, this is good for sequence. If your data is a sequence, it's very good for that. Okay, and outputs a number between 0 and 1 for each number in the cell state ct minus 1. Okay, so the output of this is a number between 0 and 1 in the cell that's ct, and then it's being multiplied by ct minus 1. 1 represent completely keep this, while a 0 represent completely get rid of this. Okay, so if the output of this is 1 multiplied by 1, then you keep it. If the over here is 0, then you forget about it. While if it's in between, then it's going to be multiplied, and it's going to be like half forgotten and half um, remember, kind of. Is that how it works? Okay, because the output of here is between 0 and 1, right? Because there's a sigmoid function here. So if it's 1, whatever over here is going to be like going to be passed through. But if it's 0, it's going to be 0 here. So it's going to be completely forgotten. So whatever the value here, if the value here is like 0.8, for example, it's going to be 0. So it's going to be completely ignored. But if the value over here, it's like between 0 and 1, then it is somehow still being remember, but it's like half remember or three-quarter remember or 1/8 remember, something like that, right? So this is like the how to forget and how to keep, kind of. Let's go back to our example of a language model trying to predict the next word based on all the previous one. In such a problem, the cell state might include the gender of the present subject so that the correct pronouns can be used. When we see a new subject, we want to forget the gender of the old subject. Okay. So what is this? Ft, it's a sigmoid of the weight multiplied by the ht minus 1 and also xt, and then plus some bias, weight of f, the weight for that specific function of t. Okay, and this is basically a linear transformation, right? We already studied this in a multi-layer perceptron or neural network, the traditional neural network, right? So weight multiplied by the input, and in this case, the input is a concatenation between the two. There's two inputs, ht minus 1 and xt, and then add bias and activate. The next step is to decide what new information we are going to store in the cell state. What new information we are going to store in the cell state. This has two parts. First, a sigmoid layer called the input get layer decides which values will update. Next, a 10H layer creates a factor. Okay, so we're looking at this now. So a sigmoid layer called the input layer, the input get layer, decide which values will update. Okay. Next, a 10H layer, this one, creates a vector of new candidate values, ct, that could be added to the state. In the next step, we'll combine these two to create an update to the state. So you combine it here. So the sigmoid layer called the input get layer decide which values will update. Okay, I'm not sure about that. In the example of our language model, we want to add the gender of the new subject to the cell state to replace the old one we are forgetting. Okay, so it is equals to the sigmoid of the weight multiplied by the concatenation of the ht minus 1 and xt plus pi. So this is exactly the same as this guy, right? Because the output of here is the same as the output of here. Right? The difference is the CT, we call a candidate values, is the 10H. Um, so the W is different. Okay, for each of this has its own W. So we have four W's. Okay, because the W is a specific to the output or to the input, because each of this has a different kind of input. For example, this one input. Well, this one is the same. Yeah, the IT is the same as FT, correct? Yeah. Eh, well, the B could be different. I don't know. I think could be different. Yeah, it's different. It looks different. Yeah, okay, different. So the CT, it's called a candidate values with WC HT minus 1 concatenated with XT plus PC. It's now time to update the old cell state CT minus 1 into the new cell state. The previous steps already decided what to do. We just need to actually do it. We multiply the old state by FT. So we're looking at this right now. It says it's now to update the old cell state. Okay, so we're multiplying by FT, forgetting the things we decided to forget earlier. Then we add IT and CT. We add them up. Yeah, we add this. This is the new candidate values, scaled by how much we decided to update its state value. Yeah, this thing is a bit complicated, the operation. Like, how on earth they know, like, they have to, like, um, multiply over here and then add it over here from the multiplication of this guy and this guy, right? That's amazing. In the case of a language model, this is where we actually drop the information about the old subject's gender and add the new information as we decided in the previous step. So CT is FT, CT, this one, the new one is FT times this guy plus whatever here, which is IT times CT. Okay. Okay, so this is the new formula, the new candidate. Um, Finally, we need to decide what we are going to output. This output, so what the hits the thing. This output will be based on our cell state, but will be a filtered version. Okay. First, we run a sigmoid layer which decides what part of the cell state we are going to output. Um, then we put the cell state through 10H. So this guy and this guy, sigmoid, okay, plus VOOT, and then goes to the multiplication. Oh, it goes to 10H first, multiplied by this guy, and then that's the output, the HT. And the output's being copied by into two different for two different purpose, two different machineries. Okay. This output will be based on our cell state, will be a filtered version. First, we run a sigmoid layer which decides what part of the cell state we are going to output. Then we put the cell state through 10H. Okay, so you're not just gonna output whatever the candidate at for that point. You're gonna um, filter it to the squashing function. After that, you are going to multiply it with the output of a neural network, basically. So so you put it through 10 hits to put the values between -1 and 1. Why -1 and 1? I have no idea. And multiply it by the output of the sigmoid state so that we only output the parts we decided to. Okay. For the language model example, since it just saw a subject, it might want to output information relevant to a verb in case that's what is coming next. For example, it might output whether the subject is singular or plural so that we know what form a verb should be conjugated into if that's what follows next. Variation on a long short-term memory. What I've described so far is pretty normal LSTM, but now not all LSTM are the same as the above. In fact, it seems like almost every paper involving LSTM uses a slightly different version. The differences are minor, but it's worth mentioning some of them. One popular LSTM variant introduced by Smith-Berger 2000 in adding peephole connections. This means that we let the get layers look at the cell state. We let the get layers, where's the get layer? So the output of this, feedback, look at the cell state. So see, this is like the get, right? This is the output of the get. You from sigmoid to a pointwise multiplication is being feedback into the neural network. Okay, it's called a peephole. Let the get layers look at the cell state as another input. So what's that? Ft is sigmoid of um, the weight of f, that particular function, uh, multiplied by the concatenation of um, the the candidates, the previous candidate, ct minus 1. See over here, uh, and then concatenated with the I don't know how you call this, hc minus 1 and the xt. Okay, that's really interesting. The get layers look at the cells. So this is the get layers. Okay, and then it, this guy is the same. So there is a concatenation. The weight is being concatenated not just with the input and the previous, um, I don't know, you call it hidden state, but it's also concatenated with the candidates, previous candidates. Okay. The above diagram adds bit poles to all the gates except for this guy. But many papers will give some bit holes, not not others. Another variation is to use coupled forget and input gates. Instead of separately deciding what to forget and what we should add new information to, we make those decisions together. We only forget when we are going to input something in its place. We only input new values to that state when we forget something older. Okay, so 1 minus. Okay, I'm not sure what is this. We make decisions together. We only forget to use coupled forget and input gates. So the output of this, instead of just going through the pointwise, it's also going through 1 minus. 1 minus whatever ft, the one here. Okay. A slightly more dramatic variation of LSTM is the gated recurrent unit. Ooh, GRU, introduced by Joe 2014. It combines the forget and input gates into a single update gate. Forget and input gates into a single update gate. It also merges the cell state and hidden state and makes some other changes. The resulting model is simpler than standard LSTM model and has been growing increasingly popular. Okay, so I have a brain fog already, kind of thing. So this ZT, so sorry guys, this is like 1 o'clock, it's sleepy time, uh, and I'm hungry. Um, so what's the difference between this and the previous one? So there's ZT, which is the sigma of WC, ST minus XT, and then the RT is, there's this guy, there's the HT, and then the HT, the hidden state 1 minus ZT times, this is HT, where is HT again? Oh, this one, 1 minus times HT plus CT, HT, ZT times HT. Plus HT minus 1 times 1 minus ZT. Okay. Oh, because this is 1 minus ZT times this guy plus over here. What's here? ZT times HT. See, it says combine the forget and input gates into a single update. Okay. How do you combine? Where is the combination? Like, this is the ordinary LSTM model, right? Yeah. It seems to be more complicated, this one. Yeah, it's like there's this thing, I'm not sure. Okay, anyway. Okay, there are only a few of the most notable STM variants. There are lots of others like def-gated RNN, and there's also a completely different approach to tackling long-term dependency like clockwork RNN. Okay, so all of this effort is just to tackle long-term dependencies, the LSN, because from what I understand, RNN is not good enough if the gap is like bigger, or it cannot remember long-term dependencies or long-term memory. Which of these variants is the best? Do the differences matter? Do a nice comparison popular variants, finding that they're all about the same. Tested more than 10,000. Oh my gosh. RNN architectures, finding some that work better than LSM on certain tasks. 10,000 RNN architectures? Oh gosh. Earlier I mentioned the remarkable results people are achieving with RNNs. Essentially, all of these are achieved using LSTM. They really work a lot better for most tasks. Written down as a set of equations, LSTMs look pretty intimidating. Hopefully, walking through them step by step in this essay has made them a bit more approachable. Yep, sure is, especially after reading this. Thank you, Chris. LSTM were a big step in what we can accomplish with RNN. It's natural to wonder, is there another big step? A common opinion among researchers is yes. There is a next step and it's attention. Oh, Okay, the idea is to let every step of an RNN pick information to look at from some larger collection of information. For example, if you're using an RNN to create a caption describing an image, it might pick a part of the image to look at for every word it outputs. In fact, Sue do exactly this. It might be a fun starting point if you want to explore attention. There's been a number of really exciting results using attention, and it seems like a lot more are around the corner. Attention is not the only exciting threat in RNN research. For example, grid LSTM by Carl Brenner, some extremely promising work using RNN in generative models such as Gregor, Chung, blah 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 also seems very interesting. The last few years have been an exciting time for recurrent neural networks, and the coming ones promise to only be more so. Okay. hmm Okay, cool. So what is attention again? It's a different variant of LSTM. Then this is the next um, big step after LSTM. Attention. The idea is to let every step of RNN pick information to look at from some larger collection of information. If you're using RNN to create a caption describing an image, it might pick a part of the image to look at every word it outputs. Okay. Anyway. Okay. Hopefully that's helpful for you guys. It's certainly been helpful for me to solidify my understanding. Until then, see you next time. Ciao.